Hello everyone and welcome to the RISE event. Our project is Laser Attack Alarm System to prevent side channel attacks and secure ICs. The continuously downscaling of CMOS technologies leads to the improvement in nearly all fields of our contemporary life. However, the advancement in integration density performance comes with the price of several new challenges. This includes leakage, short channel effects, and tunneling. Another serious trend is in increasing in the field of safety, security, and reliability related problems. Faults-based laser intrusion can be used to extract sensitive information and can initiate attacks that cause single event effects in logic circuits, which can lead to computational errors. When a laser intrusion occurs in the active region of NMOS or PMOS, electron and hole pairs are generated in the substrate due to the photoelectric effect. The electron and hole pair generation result in the high transient current flowing through the substrate and chip ground. During a laser intrusion, this substrate current rises by 10 to 100 times the normal operating condition. This changes the voltage of the internal nodes of the combination logic circuit and causes an output transient voltage known as single event transient. The transient in logic travels along the data path, causing errors in computation. A single event transient in an inverter is illustrated in the figure 1. Similarly, when the laser fault intrusion occurs in the sequential element, it causes an output voltage transient. This transient in logic is stored of the stored data permanently flips that content in the sequential storage element, leading to the loss and corruption of the data. A single event upset in case of a latch is also illustrated in the figure 2. In the established work, we can see a BBIX or a bulk built-in current sensor is illustrated in the figure 3. It is used to detect the surge in current during the laser attack. Initially, the out A node of the detection latch is set to 1 and out B node is set to 0. When a laser attack takes place, the potential at P will rises, which turns on the MN2 transistor, discharges the out A node. Similarly, in case of a laser attack, the voltage at the N well drops from VDD due to the voltage drop at the MP1 transistor. That triggers the MP2 transistor and charges the out B node that was initially set to 0, thus tripping the detection latch and indicating a laser fault injection at the output node. In the proposed design, our proposed design consists of a voltage sampling unit, a discharge unit, a precharge unit, sensing unit, and a latching circuit, as you can see in the figure 4. Here, when the substrate current increases, it is sampled in the form of voltage through this voltage sampler. The voltage is fed to the discharging unit. Discharging unit discharges the load lines that were initially set to 1 or VDD. Here, the precharge unit is also used to charge up the internal nodes of the sensing unit. Based on the value of the voltage of the sensing unit, latching circuit triggers the flag indicating a laser attack. This consists three phases of operation, namely precharge, sensing, and evaluation. In the precharge phase, the load lines 4 and 5 and the internal nodes of the sensing units are precharged to VDD. In the sensing phase, the internal nodes of the sensing unit gets coupled to the load lines, and in case of any laser intrusion, the sample voltage to facilitate the discharge of the load line and the internal node through the discharging unit. At last, in the evaluation phase, based on the discharge level suffered by the internal nodes, the output is generated by the latching circuit, indicating a laser fault intrusion. Now, to increase the detection coverage and to eliminate the effect of window masking effect in case of precharge and the evaluation phase, two detectors are used where the voltage is fed from a common voltage sampler. Now here, the precharge and evaluation phases of either of the detectors do not overlap with each other. One of the detector is thus always on the sensing phase. Now both the detectors flags are odd together to give a single detection flag, which would indicate any laser fault injection. Now here, one thing to note is that both the detectors as well as a voltage sampling unit should be shielded by a N+1 upper metal layer to avoid any laser fault intrusion in the detection arrangement itself. Now coming to the simulation results. Here, the simulations are being performed at various process corners and temperature with supply at 1.08 volts. Now to simulate the effect of laser fault intrusion and to model the photocurrent, a double exponential current topology with very short rise time and varying fall time is injected at the common node of the voltage sampling. The first graph illustrates the minimum detectable peak injected current at the common node. It is observed that with the increase in fall time, the, the required current to trigger an alarm decreases. And this is because the sample voltage would facilitate the discharge of the load lines for a longer period of time. Similarly, in the second graph, we can see that with the increase in fall time, the critical charge decreases to trigger an alarm. In this poster, we described a method to detect single event effects. A circuit and a method that is more sensitive than the existing BBX architecture is proposed. It is less affected by process and temperature variation. Also, the method does not rely on activation of a transistor to discharge a node to indicate a laser attack. Rather, it utilizes a weakly-on transistor that is operating in subthreshold region, which facilitates the discharge of the floating load lines and the internal nodes of the sensing unit to give a detection flag. Now, due to the enhanced sensitivity of the detector, it needs to be dispersed across the SoC and connected at a few places. Here are the references for further reading.